The first presentation is titled Piezo-active Suspension System for Space Interferometry and Broadband Communications by Mr. Algis Karpavicius from Kaunas University of Technology. Please.
Hello, everybody. It's a pleasure to be here, and present my presentation. So, so my name is Algis Karpavicius. I came from Lithuania, from Kaunas University of Technology, and today I would like to present to you our mission idea, Piezo-active Suspension System for Space Interferometry and Broadband Communication. In the beginning, I'll talk about introduction or heritage, which we have already seen. Targeted missions, mission goal and operational concept, target parameters, space segment, payload, which consists of two parts, orbits, time plan, and threats. Universe explorations already count decades or hundreds of years, starting with Copernicus and other predecessors. And more recently, we have very good examples of explorations, such as Wilkinson microwave anisotropy probe, Planck mission, infrared Herschel and Gaia space telescope, which actually those missions provided us with knowledge about the universe and formed the current model of cosmology, which we recently used. However, we think that not everything has been discovered yet, and there is still an area for researchers, and we think that gravitational waves exploration would be the next step. And we see that this field already attracted lots of interests from researchers around the world, and there are already two prospective missions, which are laser interferometer space antenna and Japanese mission, the Hertz missions. And the main concept of these missions are to measure gravitational waves in drag-free environment, which is quite far away from Earth. And in order to measure that, it's necessary to have very accurate pointing systems and attitude control in order to point the laser down to Earth and measure actually distances. So here we think that we could contribute. And our mission idea is to increase the accuracy of these systems by using our introduced piezo-active suspension. And we expect to increase a resolution up to 10 in power of -12 radians. We also want to establish duplex communication of laser terminal. Then also to test our suspension system using fail mission electrical propulsion thrusters or colloidal thrusters. Mission concept, so initially we are targeting to microsatellites, so we try to decrease the size as small as possible and to fit it in 50 kilograms satellite. Our satellite would be launched first to low Earth orbit or GTO, and then transferred with additional propulsion models to Earth-Moon Lagrange point 2 or hollow orbit or high elliptical orbit. Then after launch, we would establish first S-band for telemetry, communicate and command send communication, and after that we also would establish communication through laser, and after that we would measure our suspension performance with thrusters and also with laser interferometry. Our targeted parameters are based on a Gaia mission, so we saw that the accuracy of this mission was 10 in power of -10 radians, and we saw that with laser interferometry we can increase this resolution. However, the main trouble are noise and attitude control systems, which are not that soft. And So our space segment description. So space segment description would be of 5 main parts. So attitude determination control system, then power module, main processor communication module, and payload, which would consist of 2 parts. So piezo-active suspension system and laser communication. So yeah, I'll try to talk now about payload and more explicit about piezo-active suspension. So our suspension system would be, we actually propose that our suspension system would work in 2 basic ways. So the first one would be passive or semi-passive energy dissipation mode, and another one would be to implement a soft thruster response control. And absolutely the main idea of the mission is to test this suspension in real environment. And on the right side you can see some initial experiments with experiment workbench. The more rough idea of how construction would look like. So basically we would have an actuator, then we would have a main frame, and then in between we would place our suspension system, which would be controlled absolutely by controller. And in this way we would decrease the noise. Yes. And another part of payload would be laser communication. So we expect that, and it's already obvious that the demand of communication and data throughput is increasing dramatically, and that in a couple of years we will need much more capabilities. And we saw that this was demonstrated, like more faster data throughput was demonstrated by lunar laser communication demonstration last year. And we were really interested in that, and we think that our mission could contribute with this field as well, and we would like to place this module in our mission. Ground terminal. So for ground terminal, as we are going to use laser communication, so currently we don't have this type of ground system in Lithuania. So we would like to have collaboration with our space associations and departments around the globe, and we think that they could be New Mexico, California, or Spain, which were already used for lunar laser communication demonstration. Operation. So initially for telemetry and commands we would use S-band communication, which is expected to be not that fast, but after then we establish a communication with a laser, absolutely it would increase a lot, and we could gather more data from our satellite and gather more data about actually our suspension performance. Orbits. So we pointed out to you possible orbits which were quite interested to our mission. So first one would be Earth-Moon Lagrange point 2, which is actually much closer than comparing with Lagrange point 1 between Sun and Earth. In that position we could still achieve drag-free environment and test our system. And we found in literature some different ways of transfer orbits. So one of them would be ballistic orbit, and in that way time would be quite like we would use a lot of time, so almost 1 year, but we would decrease of need of delta V. And another one is high elliptical orbit, which actually is very interesting due to the long dwell time. So which can be actually even up to 12 hours. So basically it's just stands in the sky at particular position, and this way in that position we could try to point our antennas down to Earth and see the accuracy of our system. Yes, and yeah, this is the second one. And implementation. So for implementation, we are thinking to implement this mission in 32 months. Yeah, it was actually written in abstract, not here. But yeah, you can see the time schedule, and this would be implemented with collaboration between Kaunas University of Technology and Lithuanian Space Association. But we think that it's quite a big project, and yeah, probably like other researchers would like to also participate or a little bit help us. So we also think about collaboration with ESA and NASA, because they also have facilities, and this way we could have access to ground station, ground terminals, and other things. Yeah. Yeah, and top risks. So at the moment we are quite in starting position, so we still have lots of work to do. And so the first risk could be related actually to development of our suspension system, which is actually have to be proved that it's going to work in space. So we will run multiple tests, but those tests might not fully describe or test our system in realistic environment as it would be in space. So yeah, 1G gravitational environment. Then we are going to have some modules from our subcontractors, because laser communication model is already made. So yeah, and we are not targeting to development of this model. We are targeting to suspension systems. So this model would be provided by our subcontractors. So it depends on them what we are going to get. And success of our mission is very dependent on ride sharing, because to go to Lagrange point or to high elliptical orbits is quite expensive. So yeah, we also think that it would be good to collaborate with somebody to test maybe multiple modules on our satellite and share the price. And insertion to Moon Earth point, Lagrange point, requires also additional information about how to actually travel between planets, and yeah, this is something also very interesting and also quite complicated, I think. So yes, so basically this is it. And yeah, thank you for your attention, and probably questions. Yeah.
Thank you very much, Mr. Karpavicius. So, is there any question and comment for his presentation?
May I remind the audience that the questions come primarily from the reviewer team. So, it's open. Yeah, Hermann?
At the moment we are considering more piezo suspension, so not really a whole mission, which probably would quite expensive. But no, we didn't make a plan for whole mission, because we were considering few possibilities, few orbits, and fewer composition of our satellite. So like we are quite agile and yeah, adaptive for to collaborate with other. So yeah, if in that case the price would decrease, then we are probably open for that. So yeah. Yeah.
I do have a more technical question. You do have your piezo accuracy to compensate for the satellite vibration in the order of 10 to the minus 12 radian.
Mm-hmm.
The two tasks you address are gravity wave measurement or assessment and the optical communication. For both of them, you need also a basic position and attitude accuracy. Can you a little bit elaborate how you do that?
Like initial, so we are going to use like sensors of stars. Yeah.
Sensors and
yeah.
motoring. Yeah.
Yeah. So to talk about that, right? Or
yeah.
Okay.
Yeah.
So like the first thing it would be to use like additional propulsion system to actually to target to our orbit. Then in the orbit, we are expecting to use FEEP thrusters to maintain the orbit and also to point our satellite. To point actually antennas and laser to Earth or to targeted point. And attitude control would be also comprised of star sensors. And in this way, I think we would make like rough pointing to our object, depending on the star's positions. And then when we'll reach the point, the final tuning would be just with interferometry and to see how close to the middle we can get.
Well, I doubt a little bit. If you want to achieve the 40 to 660 megabit per second with your laser communication, you need to hit the antenna on ground very precisely. And this accuracy needs to be calculated and needs to be met with the technical possibilities you have on a microsatellite. So that is my question.
Mm-hmm. Yeah. So basically, the main I think feedback would be from star sensors, and then as I said, so like and then when we are pointing to Earth, maybe initially the laser one point very straight, but then we would just like final tune with thrusters and also with suspension system to see how accurate we can be.
Yeah. So you just guess that you hit the.
No, like I would say that we would calculate it from positions of stars and. Yeah.
Okay. Thank you.
Yeah.
I actually have a related question. One of the questions that I have is you're trying to measure this very small, eliminate this very small vibration, which I think is very important for the missions you're proposing. My question was, how will you verify that your suspension system is working as well as you want it to work? Are you expecting to have sensors on the spacecraft itself? Once you know it works, then you can put it on a mission and go fly and it's okay. But this is a test to find out if it's working. Do you have any thoughts on what kind of sensors you need to understand if your isolation to the levels you are? Because they were very, very small, and I didn't know how I would measure that. But I was wondering if you had thought about that.
Mm-hmm. So, like initial testing on Earth and in laboratory would be made with interferometers. I think. So we would use I think the same thrusters or to create the really finite small force to our system, and then we would measure the movements of the system, and then we will see how actually the displacement is moving, and this would be made by interferometers or capacitive capacitive displacement sensors. Yes. So this is how it would be made on Earth, and also on space we will also have feedback system. So it would also comprise of capacitive sensor or also additional interferometer, which will measure the performance of the basic suspension system movements and also how thrust is moving, and deforming our suspension system. Oh, okay.
Sorry, just wait. Okay, so I'm curious about orbital control or orbital maneuver. So you assume that into the final orbit, the rocket will carry your satellite into the final orbit, right?
We would use rocket to either GEO, or to low Earth orbit, and then additional propulsion system to go to our final orbit.
So additional propulsion system will be provided by the rocket side, not from the satellite.
Yes.
So
we are not that much yet in rocket science. Yes.
Okay. So and how your satellite can keep desired orbit.
Mhm.
For example, if the satellite is inserted into the Lagrange orbit,
Mhm.
then anyway, so the satellite should keep its current orbit.
Yeah.
That means that it needs some orbital control maneuver system. And
Yeah.
so how you can do that?
So we would do that with thrusters, basically, with onboard thrusters, and to orient and also to accelerate our satellite to the right position.
Yes.
And this would be also done with environment sensors, so like star sensors and
Yeah. So
and accelerometers and yeah.
Okay.
Like that, yeah.
so the subsystem is included in your design.
Yes, yeah. Mhm.
Okay, thank you. Mm.
Sorry, 20 minutes has passed. So I'm very sorry, but could you ask to the individually? So, yeah. Thank you very much.